In this video, we're going to look at the logistic growth function, which is something which is a slightly better model in a lot of situations than just the exponential growth function. The exponential growth function has its places, but what would happen if you, say, introduced rabbits to a certain island, let's say? Okay, the population growth of the rabbits or whatever animal, they might double every year, let's say, so it would be y equals 2 to the power of t. However, in real life, would it be possible for those rabbits to for the population of those rabbits to continue to increase? At some point, the rabbits are going to run out of food, and so at some point there's going to be a kind of slowdown in the growth of the population. They're going to reach their limit, and that's what the logistic growth function is good for. You'll see a graph of a logistic growth function down here. What happens is that, okay, at first you have quite increasing growth, but then it gradually sort of tapers off towards an asymptote, towards a kind of a horizontal line here, which would be the as far as the population, let's say, could go up. Now, logistic growth functions can be of two forms. They can be like this. You'll notice that on the bottom there's a b to the power of x term. The b would have to be a number that's between 0 and 1 in order for it to look like this kind of function here. Alternatively, it can be written like this if we want to use e in place of the b, but then we have to have e to the power of minus k times x. Okay, so there's an example of one right here. This function is equal to 5 over 1 plus 3 times 0.5 to the power of x. You'll notice that this 0.5, again, is between 0 and 1. There's a graph of it right here. You'll notice that there's an asymptote way down here at y equals 0, and an asymptote way up here at y equals 5. Another way of saying that is that the limit as x gets really, really large, like over here, when x gets really large, 6, 7, 9, 10, 100, a billion, the y value, the whole expression is getting closer and closer to 5. And as x goes towards, so that's this expression right here. The limit as x goes towards infinity of this is equal to 5. On the other hand, if x goes towards negative infinity in this direction, the y value, this whole expression, gets closer and closer to 0. Now here's another example down here, example 4, where we've got the population of a city t years after the year 2000. So for example, the year 2017, t would be equal to 17. So it's asking here what would be the population in 2000 and what would be the population in 2010. And then use a graphing calculator to determine when the population would be 500,000, when it would grow to when it would become 500,000. So let's look at that. In the year 2000, t is equal to 0, right? 0 years after 2000. And so all we have to do is to plug in 0 in place of the t. And if we do that, e to the power of 0 is going to be 1. 1 times 4, 1 times 4 is going to be 4. 4 plus 1 is going to be 5. So you would just have to do this number and that number on top divided by 5. And if you do that, what we should do when we do that is get this value here, 320,000. In 2010, t is going to be equal to 10, so we have to plug in t equal to 10 into that whole expression. If we do that, we should get 647,375 in 2010. Now, the last piece of that question was to try to predict when the population would become 500,000. So what we have to do is write the equation into y1. Right, so press y equals and enter this equation. To enter this equation on your calculator, put brackets around the bottom part and use the division sign to divide. So okay, so it's this number on top divided by, then in brackets, the 1 plus 4e to the power of negative 0.1t. And then do y2 equals this number. Graph it. You might have to change the windows, so the y max will have to be a very big number. It will have to be at least 500,000. You have to imagine how long it's going to take, so maybe you could go across to, I don't know, 50 years, if you think it's going to take 50 years to become this population, 500,000. Or if you think it's less than that, you might want to try an x max of roughly 10. In any case, if you do that, you've got your y1, this going to be looking like this. You've got your y2 looking like this. Then do second calc, intersect, press enter, enter, put the cursor over here and press enter again, and it should tell you the x value and the y value. The x value is how long it would take, so that's 5.97, so that's right at the end of 2005.